All right, good morning, everyone. So now we're in the world of data is currency, and the forefront is the AI and robotics. So now imagine one day you have this transformative idea, and you want to build a digital twin. May it be autonomous vehicle, may it be robotic, or urban planning. But in order to achieve that, you need to spend $10,000 to $20,000 just for the hardware. My name is George, and today, along with my team, Professor Ben Cheng, Associate Professor Azizur Rahman, and Associate Professor Tong-Yin Peng, we are here to tell you how we have break the paywall and then enable from super costly hardware to super cloud computing so that anyone can achieve high fidelity digital twin. So there are four main pillars to construct a high-fidelity digital twin. We have high-fidelity design, physics-based simulation, real-time monitoring and control. With our high-fidelity design, it has a detailed engineering, and this can be 2D data, 3D, real-time, historical, or static and dynamic data. And the next one would be physics-based simulation. And this is important for our detailed 3D engineering asset to obey the law of physics. Next, the real-time monitoring and control. The 3D model will only stay as a model unless it has synchronization with the digital model. So what's important is that the digital model can synchronize in real time with the real-time sensor and actuators so that the behavior will change if you change the motion of the physical world and vice versa in the digital world. And this is our first iteration when we develop an ArguVoltec digital twin. ArguVoltec is a co-location of PV system and agricultural production. And what is really important is that the study of power generation and the microclimate management. And when we were developing this first iteration, we hit three main roadblocks or challenges. The first is data integration. There are many different data types that we would be integrating into this digital twin. So you have your geospatial context, you have your CAD modeling, which is the solar panels, and you have your mesh model, which is the ocean 3D model, and as well as your historical and real-time model, where you control and monitor the solar panels. So that is one of the challenges that it requires a lot of processing to integrate all these data sets together. Second is the simulation complexity. So the platform we use is CSIM, and it is mainly used for visualization. So when you want to do any dynamic complex simulation with any physics-based simulation, it poses a challenge to us. Hence, we find an application to address this gap, and that is Nvidia Omniverse. Nvidia Omniverse is an application that enables real-time physics-based simulation. And it uses a language called OpenUSD. OpenUSD unifies different digital content creation tools format together. Includes Maya, Blender, all of the frontier digital content creation tool that you can find. So let's enable any researchers to still continue using their tools and collaborate together into one unified platform. And the application includes robotic, urban planning, autonomous vehicle, as mentioned earlier. But now we have the tools. What about the power? So when we identify the system requirement on the ideal website, it is RTX Pro 6000 Blackwell. I don't think any of you guys are familiar with this. This is a Nvidia GPU, and it is $12,000 just to get that one unit, and that's the recommended hardware. And to construct the whole workstation, you're looking at around $16,000 to $20,000. And that is our bottleneck. So we're looking for different solutions. What are the alternatives? And we found on AWS, there's this instance, G6E 2X large. and it's only $2 an hour. So we reached out to Race, and special thanks to Patrick, Dr. Patrick, and Cyrus. They helped us to set up Omniverse Nucleus server as well as Omniverse application. So this enabled us to do a really cost-effective, scalable solution for any high-fidelity digital twin. And it's a quick showcase of what we have developed, and this is the same solar tracker hardware that we saw in the earlier iteration. Excuse me. So in this demonstration, we integrate CAD modeling, BIM model, geospatial context all together, starting from modeling the physical hardware. And we model the physical hardware into CAD model and then define all of the joints and physical properties so that it reflects accurately in real world. So what you can see now is in Omniverse, and all of the joints are actually set correctly to the spring and damper ratio. And we use a special communication protocol called MQTT to synchronize the real-time, the physical asset and the virtual asset. And now we are seeing the BIM model imported in Omniverse, where enable us to do any manipulation in real time and land with ray tracing, so any simulation are highly accurate. Finally, the impact. What have we done from this RACE and EIP support? First is our food agility CRC. Now we are working with Agricultural Victoria Research to model robotic in the ocean environment. Ocean environment is extremely complex. So for robotic to design a robot and train a robot within that complex environment, it is best to design in virtual world before we deploy in real world. Second, the work with Matt, Professor Matt, the Ruby node, that we are developing the urban city. And finally, the AEA Ignite that we recently just completed with Smart Agrivoltaic, where we are evaluating the microclimate as well as the power generation using this same framework. And finally, special thanks to Mark Easton, Robert, Patrick, Cyrus, and Matt. Thank you.